This is actually an example taken from the book, so make sure you complete exercises 2A to 2C, or at least had a go at them before you look at this video. So they're talking about this one being a motion of a racing car over 10 seconds during the race. Describe what's happening. Okay, so this is the question, what's happening? Notice the car is already travelling at 44 meters per second. So if you were to draw the graph, we would start at time zero with a velocity of 44 meters per second. Because of the nature of the question, it's actually asking us to find the overall distance, the speed at the end. And you don't actually have to draw the graph for that. What we can realise is this time slot here, we are getting an area of -6 meters per second. So this is actually taking, at the end of 2 seconds, we've subtract 6 meters per second from our initial velocity, and the velocity now will be 38 meters per second. Up to time 2, we got no change. So no change, the velocity stays the same at 38 meters per second. And then going from 4 seconds to 8 seconds, again calculate the area. This is a 4 by 4, so that's 16, and that's increasing in meters per second. So that gets us back up to 4 by 4, 16, yeah, gets us up to 54 meters per second, and that's the speed at the end. You don't actually need to draw the velocity diagram for that, but we can, by knowing what's happened. If I do a squashed axis at one, so it's not the full graph, so I wouldn't use this to calculate the displacement. And again, 2, 4, 8. We start at a speed of 44. At the end of 2 seconds, we're at 38. So that was 45, 40, 48 would be about here. Let's make a nice scale for it. Minimum we need is 38. 38, 40, 42, 44, 46, 48, 52, 4. So we're going to wind up over here at the end. So we start at 44 and our velocity drops to 38. And then picks up, stays the same for 4 seconds, then accelerates up. After 8 seconds, we are doing 54. And that's the actual velocity graph for that one. Okay, so that's the second example that we can do by calculation and use it to calculate the area. And if we wanted to do the displacements, you'd calculate the area all the way to 0 of this. And remember that we're starting off fast and then it slows down. So as we draw the displacement for this one, we start off with a very quick speed, and it holds the speed quite well, and then as we get towards the end, it starts slowing down, stays constant. Starts quite fast, slowing down, stays constant, and then starts picking up again in its displacement. And that would be a displacement graph. First, so we got 2, 4, 8. If we're saying the displacement is 0 from the starting point, it's already started quite fast, and it slows down as we get to 2. Stays at the same velocity, so the gradient stays the same. And then when we get to 4, it starts accelerating, so the curve starts curving up towards the top. And if you calculate the areas of these trapezium, you can actually calculate what distance it did all of these curves at. Okay, so that's example 2.